Hi, folks. Welcome to 8.5 Polar Form of Complex Numbers. So in this series of videos, we're going to be taking a look at polar form, but specific to complex numbers. So we're not just looking at purely real numbers anymore, okay? And in this first video, we're going to focus mostly on what complex numbers are and how do we find some certain things about them, like how do we graph them and how do we find something called the modulus. All right. So let's take a look at this definition. A complex number is composed of a real part and an imaginary part, okay? So you always have a real part and you always have an imaginary part. Now, the standard form of a complex number is written in the following way, okay? We write it with a z, all right, equals a plus or minus bi. Okay. Now, this is something we've seen before, but I want to point out a few things. Okay. A, over here, A talks about the real part. And because we spend so much time in math in the real realm, we always put the real number first. Okay. So we don't want to put the I part first. We got to put the real part first. The second thing I want to draw your attention to is the B. All right, so the B is the coefficient for the imaginary part. So you have your A is the real part, B is the imaginary part. And whether you like it or not, we use this letter Z to talk about the complex number. Now, just as a side note, you'll notice that all of my Z's have the little line through them. You don't have to write them that way. The only reason I do that is because sometimes my Z's, if I don't do that, slowly become 2's, which is sort of a problem. All right. So to prevent myself from making that mistake, I just draw the little line through the Z. All right. Now, let's read this little blurb that is in the bold. All right. Numbers such as 5, 2 plus 3i, -1 plus I, and -4i. These are all complex numbers, all right? So even if I say 1, 2, 3, 4, 5, those are all complex numbers. It's just that the B part is 0, okay? So technically, we've been working with complex numbers for a very long time, just a very special kind where the imaginary part is 0, okay? All right. So let's take a look at this. How do we graph these complex numbers? Now, it turns out we can use a regular XY grid, except instead of this being X, we label this the real, okay, the real axis. And we label the Y axis the imaginary. All right. So we've got the real axis and the imaginary axis. And we plot them the same way. All right. So our A goes on the real axis and our B goes on the imaginary axis. All right. So our real is going to be the A and our imaginary, that's going to be the B. Okay. So if I look at this one, Z equals 2 minus I really have Z equals 2 minus 1I. And so what that means is -1 is my B and my A is 2. And so if I graph that on here, I'm going to go from the origin, I'm going to go over 2. That's my real. And then I'm going to go down 1 for the imaginary. So this is where the point Z is, okay? Now, what does it mean when I say find the modulus, all right? Here's what this means. The word modulus in this context means the following. Distance between Z and the origin. Okay, so in other words, I want to find out how far this point is from the origin. Okay, so check out what we're going to do. I'm going to go ahead and zoom in here, and we're going to change to a dashed line. And if I wanted to find the distance from here to here, I might even imagine it as a horizontal situation and a vertical situation. And then the distance is really, is that a hypotenuse? It sure is, right? So we have this hypotenuse. We're trying to find the length of the hypotenuse is really what we're doing when we're finding the modulus, okay? So let's talk about it in symbols. When I say modulus, we're going to write those absolute value bars. But the absolute value bars tell us about, say, find the distance. They don't mean find the absolute value, okay? So we find the distance, and all we're going to do is plug it into our Pythagorean theorem. So square root of 2 squared plus -1 squared. We do a little arithmetic. 2 squared is 4 plus -1 squared is 1, and we get square root of 5, okay? So in other words, our modulus here, our modulus is square root of 5. Or on our diagram, that corresponds to this line, that distance having a length of square root of 5. Okay. So not so bad. Let's go ahead and try example 2. Okay. Same thing. We've got a real part. We've got an imaginary part. Let's figure out what those are. Our imaginary part is +2. Our real part is 3. And so if we graph that now, from here, from the origin, we're going to go 1, 2, 3. And from there, we're going to go 1, 2. Okay. So my final place for my z in this diagram is over here. And again, if I change to the dashed line, I can think really to find the modulus, I want to go from here to here. But we can use what we know about right triangles and instead find this leg and find this leg so that we can use those in the Pythagorean theorem to find the length of that hypotenuse. Okay, so to find the modulus, we're going to put it in the proper notation with the absolute value bars, equals the square root of 3 squared plus 2 squared. Those are our x and y values, or our real and imaginary values. And we're going to do a little computation. 9 plus 4, and we get square root of 13 is the modulus, or rather the distance from that point to the origin. Okay. Now, if we wanted to write an equation for the modulus in general, maybe we go ahead and stick that down here at the bottom, that the modulus we find using square root of a squared plus b squared. Okay, and those are exactly our a and our b from our imaginary and real parts of our complex number. All right, so let's get that color-coded in the orange. All right, now we have 2 more examples here. I think that's a good thing for you to try on your own and see how you do, okay? Feel free to come check in with me if you'd like to make sure your answers are correct, but I think those would be good as some extra practice, all right? So we're going to cut the video here, and when we come back in part 2, we'll talk about the polar form of the complex number and how we sort of do different things with that, all right? See you back here.